Hello and welcome back to Radiography Simplified. Michael here. In our previous video, we talked about the types of radiation and highlighted some points on how particulate radiation interacts. In this video, we'll expand things by looking at how radiation interacts specifically with matter. Much of our focus will be on X-rays, as these are more common in diagnostic radiography. Three common interactions that occur between electromagnetic radiation such as X-rays and matter include photoelectric effect, Compton scattering, and pair production. First, the photoelectric effect. This commonly occurs at X-ray photon energies up to 100 kiloelectron volts. This range of kiloelectron volts is known as the diagnostic energy level, because this is the range of X-ray energy utilized in diagnostic imaging. Interactions of radiation have requirements, which are certain conditions that must be satisfied before they can occur. In the case of the photoelectric effect, a key requirement is that the X-ray photon must have an energy that exceeds the binding energy of an orbital electron in the atom that it interacts with, which in the case of diagnostic imaging is an atom in the patient's body. When this requirement is met, the photoelectric effect could occur. Now, what does the photoelectric effect entail? Basically, an incoming X-ray photon ejects a K-shell electron in the atom of the target matter or patient in our case. The X-ray photon is then completely absorbed by the atom, as it no longer has enough energy to leave. The photoelectric effect is responsible for image production in X-ray imaging. As for Compton scattering, it is more likely to occur at an energy level that is above that of the photoelectric effect. The Compton range is 100 kiloelectron volts to 10 megaelectron volts. Compton scatter occurs specifically between incident photons and outer shell electrons of an atom. Because outer shell electrons are lightly bound, when an X-ray photon collides with one of them, the electron is ejected and the photon changes in direction. This electron has enough energy to exit the patient. The photon, which is changed in direction, is called a scattered photon, and it also has enough energy to exit the patient. Now, this part really affects diagnostic imaging, because as it leaves the patient, the scattered photon can proceed in the direction of the image receptor, fogging the radiographic image and reducing image contrast. Or, it could move in the direction of someone in the X-ray room and get absorbed by this individual. This is why Compton scattering is known to be responsible for occupational dose. Pair production occurs at levels way above the diagnostic range, but it's still worth talking about. In pair production, a high-energy photon interacts with a nearby nucleus to create a positron-electron pair. The positron collides with the electron and gets annihilated, producing two photons. Now we conclude by briefly talking about the interactions in particulate radiation. As we stated in the last video, high-charge particles like alpha particles are able to lose their energy rapidly through Coulombic interactions. The efficiency of these interactions is proportional to their charge. That concludes the section on interactions of radiation with matter. If you want more insight into this, check out this video on X-ray production and interactions, which goes into more detail. Next up, we talk about the direct and indirect actions of radiation. See you next time.